All right, hello, and thanks for tuning into this video today. I am now in Pittsburgh, and I'm recording from my hotel room. Uh, I want to go spend a couple lectures covering some statistical foundations, and so we've been doing a lot of statistical kind of just some statistical summaries and data visualizations, which is important. And I also introduced a couple statistical tests like the t-test and the proportion test, which allow us to distinguish between actual phenomena and random flukes. And now I wanted to just take a little bit of time on talking about some of the theory behind those statistical tests. And so we're going to have to cover a couple topics like the normal distribution and the sampling process, and then eventually we'll get to the central limit theorem. So, the normal distribution is a probability distribution, and that will serve as kind of the starting point, because when we make it to the central limit theorem, we tie everything back to the normal distribution. Sampling is how we gather the data from our population, and because of that random sampling process, we end up with something called a sampling distribution. And so let's start off by talking about the normal distribution. The normal distribution is what we often refer to as the bell curve, and it is a probability distribution, which means it describes the probabilities that you will get different values. Okay, what is pictured here is the standard normal distribution, which is centered at 0 and has a standard deviation of 1. The normal distribution has a single peak, looks like just a hill, and it is symmetric around this middle point. Because it is tall in the middle, that means values that are drawn near the middle appear most frequently. So for the standard normal distribution, the values around 0 are the most common and most frequent values. And as you go higher up, okay, so like 1, around 1, or around -1, it's not as common. As you go even farther to, say, +2 or around -2, it gets even less common. And then if you go out to, say, +4 or -4, those become very, very, very rare. Okay. A key thing about any probability distribution is that if you were to shade in the area underneath the curve, the total area would equal 1, and that represents having a 100% probability, total probability of 1. Okay. So, what I showed you was the standard normal distribution. This is also known as the z distribution. The mean of the standard normal distribution is 0. The symbol we use for the mean is the Greek letter mu, and the standard deviation is 1. And the symbol we use for the standard deviation is the Greek letter sigma. One thing that might be a little bit tough to wrap our head around is that it is a continuous distribution, and so the probability of getting any single exact value, okay, that is, you get the exact value where it matches infinitely many decimal places, the probability of getting some exact value is going to be 0. And so we only talk about probabilities over some kind of range or an interval. So rather than saying, what is the probability we get the number 0 exactly, we might ask, what's the probability we get a number between 0 and 1? Or what's the probability we get a number greater than 1? Or as a start, we can just say, what is the probability that when we draw a random value of z from the standard normal distribution, what is the probability that the value of z is going to be less than 0? Okay. Well, our answer is going to be 1/2, because here is our diagram, and 0 is in the middle, and so I'm going to draw a line at 0, and we're going to shade everything to the left, and this represents what is the probability of getting anything less than 0. And we can see that if the total area under the curve is 1, we have shaded exactly half of that, and so our answer is going to be 0.5. Okay. Conversely, if I said, hey, what is the probability that we get a z greater than or equal to 0? Okay, what is the probability that we get a z greater than or equal to 0? Then our answer is also going to be 0.5. Okay, we know that the total area under the curve is 1, and on the previous slide we said the area to the left of 0 is 1/2, and therefore the area to the right of 0 is also going to be 1/2. Okay, and whether we use the probability that z is greater than or equal to 0 or the probability that z is greater than 0, those answers are both going to be exactly 0.5, because the probability of getting exactly 0, that is 0.00000 with infinitely many zeros, the probability of getting that exact value is 0. And so we don't have to worry about getting any exact number, right? It's kind of like if you, if I say, name a random number, okay, and you need to name infinitely many digits, right? So you start off and you say, hey, the first digit is 3, and then the next digit is 1. And what is the probability that if you name infinitely many digits, you will match all the digits of pi exactly, okay? And the probability of that happening, the probability of getting that exact value is 0, okay? So in a continuous distribution, the probability of getting an exact value is 0. When it's a discrete distribution, when we're talking about like whole numbers, of course you can get some exact values, but for a continuous one with infinitely many decimal places, probability of getting an exact value is going to be 0. All right, there are 3 numbers that are very kind of important, I would say, to remember regarding the normal distribution, and these 3 numbers are 68, 95, 99.7, and this forms what we call the empirical rule, or in some cases we just call it the 68, 95, 99.7 rule. And that is to say that if you were to mark on your normal distribution going up 1 standard deviation and going down 1 standard deviation, okay? So if you think about the standard normal distribution, if you have it centered at 0 and you go up 1 and down -1, the area in between +1 and -1 is going to be approximately 68%, okay? And then if you go from +2 down to -2, the area in this region, okay, and you can see it covers the majority of it, that covers 95%. The probability that z is going to be between 2 and -2 is around 95%. And then if you go up 3 and down to -3, you get almost everything. You just see this tiniest little sliver above 3 and the tiniest little sliver below 3. If you go from 3 to -3, you cover 99.7%. So almost 100%, not quite, but almost. And so that's the empirical rule. Sometimes we are asked, what is the probability that z is going to be, say, less than, some arbitrary number, okay? And in the past, we would have to use a z table. If you pick up a traditional statistics textbook, in the back of the textbook, there's going to be a bunch of tables, and one of them is going to be the z table. But now we can just use R, and the function we use is p-norm, and you just type in the z value, okay? And when you do that, it's going to give you the area to the left of the z value under the standard normal curve. So if I say, what proportion of values have z less than 0.42, okay, or in other words, what's the probability that z is less than 0.42, we can type that into R by asking p-norm of 0.42, okay? So the diagram here, again, the total area under the curve is 1, and you can see we are at positive 0.42, so we've shaded in purple a little bit more than a half. Exactly how much? Yeah, eyeballing something around 60 something percent. And so if you type in p norm 0.42, it says around 66%. So this purple area is around 66.6627, so around 66.28% is less than 0.42. Okay. Now, one thing to remember is that when you type in p norm, it's always going to give you the area to the left. If you want the area to the right, you can subtract that value from p norm. So if I say, hey, what is the area in lime green? What is the area that, what is the probability that z is greater than 0.42? Okay, then we could just do 1 minus the area to the left. 1 minus p norm of 0.42, and we would get 0.3372. Okay. Another option is within the p norm function itself, you can change one of the arguments, and the default is to calculate the lower tail, but you can say, I don't want the lower tail. You can say lower.tail is false, and this will give you the upper tail, and that will give you the same value of 0.3372. So again, by default, it will give you the area to the left. If you want the area to the right, you can do 1 minus p norm, or p norm with lower.tail equal to false. Another thing is that the normal distribution is symmetric, okay? And so if you calculate what is the area to the left of some value, like negative a, that's going to be equal to this area to the right of positive a. So, if I say, hey, what is the area to the left of negative 1.04? Okay, so I don't have a diagram here. But basically, if I say, hey, imagine this is at negative 1.04, and I shade the area to the left of negative 1, we can see because of symmetry, it would be also equal. The area to the left of negative 1 would be equal to the area to the right of positive 1, or in our case, I think we're doing negative 1.04. The area to the left tail over there, would be equal to the area to the right of positive 1.04. And we can see that's going to be the case. I could say p norm of negative 1.04, and I get 0.1492. I can say p norm of positive 1.04 with lower tail equal false, and I get the same value, 0.1492. Or I could do 1 minus p norm of positive 1.04, and I would also get the same value, 0.1492. And that's because the normal distribution is symmetric. We can generalize the normal distribution from the standard normal to any other kind of normal distribution that might exist in the real world. So a lot of variables in the real world are approximately normal, but their mean probably isn't going to be 0 and with standard deviation 1. So, but they'll have a different mean and different standard deviation, but they'll still kind of follow the overall shape of the normal distribution. So, for example, if you look at the heights of adult men in the United States, the distribution of heights is approximately normal, where the mean is around 69.5 inches and the standard deviation is around 3 inches. Okay, so it's not exactly that, but these numbers are pretty close. 69.5 is around, is 5'9.5" in centimeters. What is that? 69.5 it's around 176, 177 centimeters, something around there. Okay, and standard deviation of around 3. So we could ask this question: what proportion of U.S. adult men are shorter than 72 inches? So in our diagram, we're going to put 69.5 right in the center. 72 inches is a little bit above that, okay? It's 2.5 inches above the mean. And I'm going to draw a line right there, and I'm going to say, hey, what is the probability that we get a value less than 72? So we're asking, what's the area to the left of 72 in this normal distribution? So what we want to do is we want to convert to what we call a z-score. Okay, a z-score is going to measure how many standard deviations an observation is from the mean. So our mean is at 69.5, and our observation, or our cutoff line, is at 72. Each standard deviation is 3. So if I had cut it off at 72.5, I would have been exactly 1 standard deviation above the mean at 72.5, and so my z-score would have been 1. We're not quite at 72.5. We're at 72, which is a little bit less than 1 standard deviation. And so I would say, all right, what is that distance, or how many standard deviations is that? I'm going to do 2.5 divided by the size of my standard deviation, 3, which is 0.83333. Okay, so the formula for the z-score is, you take your observation or your measurement, your cutoff line, whatever it is, you subtract off the mean to get the distance from the mean, but you want not the direct distance, but how many standard deviations that is. So you're going to take that distance and you're going to divide by the size of your standard deviation, sigma. So asking what is the probability that the height is less than 72 is equivalent to asking what is the probability of getting a z that is less than 0.833. And so we can plug this in to p norm. Okay, we type in p norm of 0.8333, and our answer is going to be 0.7976. So, around 80%. Around 80% of U.S. adult men are going to be, shorter than 72 inches. You can also use p norm directly, right? So rather than, calculating the z-score yourself, and z-scores are handy because it allows you to compare observations from different samples and different distributions. So for example, you can compare what's more unusual, a man who is 6'4" or a woman who is 6'1" or something like that. Okay, and you can calculate the z-score, right? So we'd say these would both be considered tall. Okay, and if you calculate the z-score, probably the compared to other adults in the United States, probably the woman who is 6'1", it would be considered more unusually tall compared to a man who is 6'4" or something like that. Okay, so that's just kind of a way you can compare observations from different distributions. But anyway, you can type in the values directly. So you can say p norm 72 inches, where the mean is equal to 69.5. So we want to know what's the probability of getting something less than 72 if the mean is 69.5 and the standard deviation is 3. And this gives us the value, 0.7976. This is technically a little bit more accurate because here we had to do a little bit of rounding off, 0.8333. And if I kept even more decimal places, so this says 0.797662, and this is 0.79767. So this is technically a touch more accurate, but again, it's not like the heights of adult men in the U.S. are exactly the normal distribution, follow the normal distribution exactly. So it's an approximation, and it's going to be pretty good either way, I think. Sometimes we want to work backwards, okay? And so so in this case, we can say, I want to find the 98th percentile. I want to find what is this measurement here so that the area to the left is equal to 98%. So for example, we can say head circumferences, that if you measure the circumference of someone's head, I made up these numbers, but let's say the mean head circumference is 23 inches and the standard deviation is 0.8 inches. Okay, the mean is 23 and the standard deviation is 0.8. And what we want to know, so if I say what is the 50th percentile, the 50th percentile would be 23 inches, because that would be the location where exactly half are below and half are above. Here I want the 98th percentile. So I want to know what is the location where 98% of head circumferences are going to be less than whatever number. Okay, so in order to figure this out, we use a function called qnorm. Okay, qnorm is going to give you the value of x, so that the probability is going to be less than that number. Okay, so over here we have pnorm to calculate the area to the left, and then qnorm, you give it the area and it will give you the corresponding value. So first we can find what is the z-score that will give us an area to the left of 0.98. Okay, and we say qnorm of 0.98, and the number it spits out is going to be 2.05. So if I plug in z is equal to 2.05, we're going to get 0.98. Okay, so qnorm and pnorm are like inverse operations. If you type in pnorm of 2.05, you get 0.98. If you type in qnorm of 0.98, you get 2.05. Okay, or I guess more precisely 2.0537. Okay, and then now that we have the z-score, we have to convert this back to head circumferences. So I'm going to just use algebra, and I'm going to say z is equal to our head circumference minus the mean divided by our standard deviation. And so if I solve for x, then I would multiply both sides by sigma, okay, and I would get z times sigma is equal to x minus mu. Then I would add mu to both sides, and this would tell us that x is equal to mu plus z times sigma. So this is just kind of using algebra to get back to our original value. And so if the mean is 23 and my z-score is 2.0537 and my head circumference standard deviation is 0.8, then the x comes out to be 24.64, right? So if you do 23 plus 2.0537 times 0.8, we're going to get 24.64. So looking at this diagram, that's right here. If I draw a cutoff line at 24.64, the area to the left of that is going to be 0.98. Okay, again, you can do it directly. So you can type in qnorm, and we want to get the corresponding 98th percentile where the mean is 23 and the standard deviation is 0.8. And if you do that, qnorm comes back and says your answer is 24.643, which matches what we got. Okay. Let's say you wanted something below the average, right? So let's say we want to have hats fit 96% of people, the middle 96% of people. And so we are going to, if we want the middle 96%, we're going to exclude the bottom 2% and we'll exclude the top 2%. So the 98th percentile, it kind of is the cutoff between the top 2% and everyone else. And then we'll find the second percentile, which will cut off the bottom 2% and separate that from everywhere else. So we can do this using qnorm, and we can do qnorm of 0.02, where the mean is 23 and the standard deviation is 0.8, and we'll get 21.357. Again, this is, we could have just used a little bit of math to figure this out as well, because the normal distribution is symmetric, and if our center is at 23, if the 98th percentile is basically 1.643 inches above the mean of 23, I could have also gone 1.643 inches below the mean of 23, and I would have also gotten 21.357. So the the largest size is going to be 24.64, and then the smallest 2% will be at 21.357. So if you want the middle 96%, you'll go from around 21.36 to 24.64. All right, let's talk about samples and sampling. And so this is how we select observations from the population. So, whatever research question we have, the population is going to be everybody, the entire group of all the individuals or items that are relevant to whatever research question we have. The issue is that our population is going to be too big for us to study directly. There's just going to be too many people. So examples of populations will be like all the voters in a country, right? There might be millions, right? And we just can't track them all down, okay? All stars in our galaxy or something. A sample is going to be a subset, just a selection of the population that we actually observe and gather data from. So maybe we survey 1,000 voters, okay, hopefully that are representative of the population, or we select 50 stars and we observe those, okay? And so that's going to form our observed data. So whatever information we record from the sample that's selected, that's our observed data. And then what we do in statistics is we use the sample data to try to make inferences about the population. Okay. When we are talking about the population and we're describing the population, the numeric summaries that describe a population are known as parameters. Okay. So if we're talking about all adult women, that would be the population would be all adult women, and then the true average height, okay, the average height of all adult women, that would be a parameter, okay? If our population is all voters, okay, then perhaps the parameter that we're interested in is the proportion of all voters that support a particular candidate, okay? And the thing is the parameters are generally unknown to us because they relate to the population, and again, the population is too big for us to observe directly. And so it's unknown, but we want to try to estimate it. And so what we have to do is we look at our sample and we have a numeric summary from our sample, and that's going to be calculated from our observed data. And we use our sample statistic to then estimate population parameters. So perhaps we get a sample of 100 women, and we get the average height of those people in our sample. That would be a statistic, okay? Or perhaps we surveyed 500 people, and we asked them, do you support this particular candidate, yes or no? And we can get the proportion, maybe 46% answered yes to supporting that candidate. And so statistical inference is the process of going from the sample statistic to basically making educated guesses, or for us to draw conclusions about the unknown population parameters. So again, an example is if you do a political poll, the population would be all likely voters in the upcoming election. Your sample might be, you surveyed 800 people. The statistic is that in the sample, 44% support a particular candidate, candidate A. That's your sample proportion. And the inference is we're going to try to estimate, okay, we use this 44% value from our sample to estimate the true proportion of all likely voters who support candidate A in the population. Another example is, you can imagine a pharmaceutical company trying to create blood pressure medication. The population here would be everybody with high blood pressure who might use this medication, and you get data from a sample, and your sample might be 50 volunteers who have high blood pressure. Half of the people get medication, half of the people get placebo. And so the sample, you calculate statistics based on your sample. The mean blood pressure of people who took the medication might be 125. That's a sample statistic. The mean blood pressure of people who got the placebo maybe is 135 for systolic blood pressure or something. And then, so you have the difference between these means is 10 points. And so the inference is, okay, we're going to use this 10-point difference to estimate the true average difference in blood pressure if everyone in the population were to take medication versus placebo. So this would be the difference in population means. In order to help us keep track of which one's which and not get us mixed up, we have different symbols. Okay, so when we're dealing with the mean of a sample, we call it y bar. Okay, and if we're dealing with the mean of a population, we call it mu. Standard deviation of a sample is S. Standard deviation of a population is sigma. The proportion of a sample is p hat, and the proportion of a population is p. Sometimes you see the pi. The correlation of a sample is R. Correlation in a population is, it looks like a p, but it's the Greek letter rho. And then say if you're doing regression or something, you calculate a slope, in the sample, your calculated slope would be b1, and then for the corresponding population parameter, it'd be beta 1, okay? Kind of in general, population parameters, we use Greek letters, with the exception of maybe proportions, and for samples, we use just Latin letters. Okay. Sampling is that process of selecting the individuals from the population to form a sample. And our goal is that we get a representative sample, a sample that looks kind of like a miniature version of the population, okay? A sample that is not representative is said to be biased, okay? Biased here just means your sample is not representative of the population. It doesn't necessarily mean that there's malicious intent behind collecting the sample. I mean, there could be, but that's not necessarily the case. It just means your sample is not representative of the population. Now, one method that should produce a representative sample, not guaranteed, is simple random sampling. And that means every individual in the population has an equal chance of being selected, and you just randomly select them, individuals one at a time. And then another aspect of simple random sampling is that every possible sample has an equal chance of being selected, which is kind of a weird thing, but you think of like a lottery ticket. Basically, every single number has an equal chance of being selected, and any combination of numbers has the exact same probability of being selected. Now, simple random sampling should produce representative samples, but again, because it's random, it might not be representative of the population because of just kind of random chance. Okay, and so, once we establish these kind of terminologies, we can talk about sampling distributions. And the idea is that when you do random samples, you're going to get random individuals selected. And so if you take multiple random samples, then the individuals that are selected in each of your samples are going to be different. And so your sample statistics, okay, are going to vary from one sample to another. So let's say in the population, all right, exam scores are normally distributed, and probably not, but let's just say in this example, in the population, the scores are normally distributed where the mean is 75, and we have a standard deviation of 10. If you draw 20 random values, you might get an average of your 20 people to be 73.5. Okay? If someone else draws 20 random values from the population, their average could end up being a little bit different, 76.1. Someone else draws 20 random values from the population, perhaps their average is 74.9. Okay? Each of these values is kind of like an estimate of this population mean, okay? But they differ from one sample to another. And so if you keep that in mind, some of these sample values are going to be more likely and other sample values will be less likely, okay? So imagine another population where the mean is 16 and the standard deviation is 5, okay? So again, if the mean is 16, 68% of values that we draw will be within one standard deviation of the mean, so between 11 and 21. 95% will be within 2, so between 6 and 26. And 99.7, okay, almost 100% will be within 3 standard deviations, so between 1 and 31, okay? And we're going to draw random samples of 5 values. So we expect the sample mean of our sample of 5 values to be close to 16, but we also expect, values that are a little bit different. So could we get a random sample where the average is around 15, average of the 5 random values around 15? Yeah, that sure sounds like it could happen. Could I get 5 random people drawn from this population? Again, the mean of the population is 16. And is it possible where I draw 5 random people and the average is only 14? Okay, and that also seems possible, but not as common as getting, say, an average of around 15. Okay, could we draw 5 random values where the average is only 12? Okay, and now that starts to feel unlikely. Okay, what about 5 random values from this population? Again, the population has a mean of 16, but could you get 5 random values where the average is only 8? And that seems really unlikely to happen. Or the average, a sample where the average is only 3. And that seems extremely unlikely. I almost want to say it's impossible, but again, we don't like to use the word impossible in statistics. And basically the idea here is that the more if you're going to say my sample is going to be very, very, very different from the population, that seems less and less likely to happen, okay? So the sampling distribution kind of takes this intuition that we have and, formalizes it. Basically, rather than us saying, sure, values around 16 are going to be more likely. Samples where the average, the mean of your sample is around 16 is going to be more likely, we can kind of formalize, what we're trying to say with a sampling distribution. So a sampling distribution is the probability distribution of a sample statistic like y bar or p hat or whatever it might be if we were to draw all possible samples of a particular size n from the population. And so the sampling distribution is going to tell us what values the statistic can take and also how often those values might occur. So for the sample mean y bar, we would create the sampling distribution of the sample mean or the sampling distribution of y bar. So to demonstrate this, we can simulate this by kind of defining a population, and then we're going to actually randomly draw a random sample of a given size. And we're going to do this again and again and again. Each time I draw a random sample, I'm going to calculate a statistic. In our case, we'll calculate the mean of the sample. And we will keep track of all of these things and make a little histogram, okay? And there's this little website that we can use. And so, let me see if I can. So this here, up here, represents our population. It is normally distributed with a mean of 16, standard deviation of 5. and I'm going to draw samples of size 5. And so here I'm going to click animated, and we're going to draw 5 random values from this population. We got 1, 2, 3, 4, 5. I'm going to calculate what is the mean of these 5 values, and the mean of these 5 values is right here. Okay, I'm going to do this again. Okay, here's 5 random values. The average ends up being down there. Okay, 5 random values. The average is right there. Another 5 values, and the average ends up being there. And I can kind of repeat this over and over and over again. And every time I'm getting a different sample of 5 random values, but we're going to calculate the average of those 5 values. Okay, and I can do this again and again, but I can kind of speed things up by just doing like 5 at a time. And so, we're doing a few at a time. And so after doing, say, 244 of these, this is kind of the spread of the different samples that we're getting. So again, here's 5 values, and we're just kind of, once we calculate the average of the 5, you can see a little blue brick dropping down a tiny little bit here, and then I can kind of fast forward, and I can just do like 10,000 or 100,000, and this is the resulting distribution. Okay, so we end up getting a this is what we would call our sampling distribution of means when our sample is size 5. If I take a bigger sample, say n equal to 16, okay, then what happens is I'm drawing a whole bunch of these values. The animated takes a long time because I have to draw 16 random values, and I'm going to calculate the mean of all 16 of those random values. Okay, and I'm going to do this just like one more time here. 16 random values, I'm going to calculate the mean, and the mean of 16 values ends up right there. And if I do this again and again and again and again and again, this is kind of my distribution. I'm going to fast forward, and here it is after around, I guess, 180,000 random values. This is our distribution. And so just kind of comparing the sampling distribution when n is equal to 16 versus the sampling distribution when n is equal to 5, what we see is that the sampling distribution, when you only have 5, has wider spread, okay? And when you have n equal to 16, this spread is less. You can even see standard deviation is around 1.26, n equal to 5, the standard deviation is around 2.24, okay? And there's this inverse relationship where when you take a bigger sample, you end up having less spread in the sampling distribution. When you have a smaller sample, you end up having more spread, okay? So think about this. Like if I take a sample of only 2, I'm going to end up having quite a bit of spread. I'm going to have a standard deviation of 3.54. And the reason for that, okay, is when I take only samples of size 2, it's not that weird. So I just clicked animated. It's not that unusual for me to get 2 random values where both of the values are kind of low, and the average of those 2 values is down here, okay? Here I got one really high and one kind of low value, and so the average ended up in the middle-ish. 2 values right here, kind of around here. But again, it's not going to be too weird to get 2 random values that are high, okay, or 2 random values that are kind of low, and for your average to be kind of end up far away. Let me see if I can get like a really high sample mean. It's just not happening. Okay, but again, just doing a whole bunch of these things, it's not that unusual to get 2 random values where the average ends up being quite high. Okay, so you end up having a lot of spread. But when you take, say, samples of size 16, even if you get one individual that's really low or one individual really high, when you average all of them, okay, overall, most of the other, 14 values or 15 values, even if you have one really low value, are going to be kind of in the middle, and so the average of all of them ends up kind of in the middle. So yes, in a sample of 16, you might get an individual who's really high or an individual who's really low, but when you average them all together, the average kind of ends up close to the middle. So here we got a fairly high individual, but also a fairly low individual, so they kind of cancel out, and so the average ends up being kind of like right in the middle. And so, the probability where all 16 are going to have an average that's really low, or all 16 will have an average that's really high, is really unusual. And so when you do a whole bunch of these things, the spread of the different sample means ends up being quite small. So this so this is kind of the diagram schematic of what we're doing, is that we have this population, okay, and what we're going to do is from the population we draw a random sample and we calculate the mean of that sample. We draw another random sample, calculate the mean, draw another random sample, all of the same size. We're calculating the mean, and we get a sense of the different kind of y bar values that we can get, okay. And so, what happens to the distribution of the sample means as the sample size increases, okay? What we end up seeing is that the center of the distribution kind of stays close to 16. And the spread, all right, of the distribution gets smaller as n increases. And then the other thing is that the shape of all of the sampling distribution remains normal. And so if I tried it out for n equal to 2 or 5 or 10 or 16, what we see is that all of them stay centered around 16, okay? But what we see is that the amount of spread gets smaller and smaller and smaller as our sample size increases. Okay, we could also run some code in R to do this, and we can try it out with different kinds of populations. We don't necessarily have to start with a normally distributed population. But here I'm going to run out of time, so we'll continue this on in our next lecture. But thanks for tuning in. I don't have any lecture view quiz questions for today, but I'll my next lecture perhaps I'll put some in. But we'll pause here and we'll continue on